Okay. Think. Yeah. Okay. Sound should be working. Yeah. Okay. Sound should be working. Yeah. Okay. Sound should be working. Oh. Stream going in the background, so hopefully it doesn't repeat too much. Um. Okay. Cool. I'll give it a few minutes for people to join and such. You can all hear me, right? I think you should be able to, but just to be sure. Cool. I'll probably properly get started at 2:20 just to give a little bit of leeway room before I jump into it because I'm gonna try and go a bit faster than last time. Oh, and then the VOD will still be um, available for this as well. Mm-hmm. Okay. Okay. All right. Let's go ahead and get started. Oh, wait. Yep. Don't pay attention to that. That's gonna help me to do this quicker. All right. Let's see. Check this. Double check that. All's good to go. Lovely. Okay. I think this will take a second. Can you all see that? You should be able to. How do I do a slideshow? Bro. Oof. Why is it doing in this one? There we go. Cool. Okay. I need to pull that up. Okay, why are we doing this? Hold on. Not entirely sure why. Why is it using both of my displays? I don't want you doing that. All right, give me 1 second. I'm just gonna move this over here because at least I know how to use it through here, and it's not gonna do that. Here. Boom. There we go. Upload that. There we go. Now this should work better. There we go. There we go. All right. Now we're good to go. Sorry. Okay. Hello, everyone, and welcome to exam 3, the review section of the review and AMA. Just a quick overview. If you weren't here for the exam 2, review and AMA, this will just be a quick run through. I organize it a little bit differently this time around to focus more on explaining things on my end to you all. And then you can still ask questions throughout, of course, and I'll answer them. But I'm kind of going to go by bulk sections. And at the very end, we'll have a few practice problems and we'll go through them together. Yeah. And then after that, we will have the AMA where me and at least 2 other TAs will play some game or something and have the chat open, and any remaining questions that you have, throw them in there, and we'll answer them to the best of our ability. Okay. All right, let's get started. So things that are going to be covered on this exam are what I would consider foundational items for OOP. Sort of arguably the whole point of you guys taking this class is to learn about things like dynamic binding, polymorphism, inheritance, that sort of stuff, because it's extremely useful and it passes over pretty much if you are a CS major or if you're getting a CS minor, you're never going to get away from this, right? Good code is that's a backbone of it. It's being able to leverage things like dynamic binding, polymorphism, and then also being very aware of algorithm design and efficiency, which is where we're talking about these sorts that we've been teaching you so far, these searching algorithms as well, and then the ADTs that we've exposed you to so far. So yeah, let's jump right into it, or not, or I have to click it. That's great too. Again, just a brief overview. Exactly what it is that I'm going to go through with you guys is abstract classes and final, polymorphism, dynamic binding, interfaces including comparable and casting, recursive and linked structures. So that's just a merged way of talking about merge sort and recursion at the same time, since merge sort uses recursion. ADTs and list ADT. So the list ADT, of course, is linked list, array list. You can have set list as well. There's different kinds. And then more ones that you don't really know too much about, where we're talking about stack, queue, tree, that sort of stuff. You don't need to be too aware of it, but it's good to understand the purpose of ADTs just to be privy to them. So, and then more specifically, linkless, iterable, and iterator. Also, array list and generics, which you guys have been working with for a little bit now. So that shouldn't be too difficult for you. Asymptotic growth. So that's just the big O stuff. Searching and elementary sort. Sorry, I forgot that I put that there. I don't mean that as a dig. This is just meant as like an introduction to sorting. That's the only reason I put it there. And then exceptions, bounded wildcards. So again, wildcard generics, that's that question mark. File input and output, and mixed practice at the very end. So why are my arrow keys not working? Now they're working. Okay. Weird. All right. So to start off with, abstract classes and the final keyword. These two things control how inheritance is used, or ways of controlling how it's used, and how much behavior subclasses may customize and leverage from it. So an abstract class. What is an abstract class? Well, you can think of it as a partial blueprint. You cannot necessarily create an object directly from it, right? That's kind of the whole point of it being abstract. It's that it is something for you to follow as an idea. It's not something that should necessarily be something that you want to represent as a concrete object, because it wouldn't really make sense. But with it being a sort of partial blueprint, you definitely want to still be able to define fields, concrete methods, constructors, abstract methods as well, of course, that subclasses absolutely have to have. So again, that's just guaranteeing some kind of behavior. And then you can use it when related classes share state or helper methods, but they still need class-specific behavior. It's just talking about the sort of subclasses in that area where they need to have some sort of predefined behavior from that abstract class, but they also have their own behavior that they normally are defining with a few abstract methods inside of an abstract class. You don't have to have abstract methods in an abstract class. It's not necessary, but it normally is the case. To have an abstract class and not have abstract methods is a little odd, but the utilization of abstract to just make it so that class cannot be directly instantiated is perfectly fine. If a subclass does not implement every abstract method, that subclass must also be abstract. Yes, that is true. If another important point there is, if you had, let's say you have an abstract animal class, right? And you have two abstract methods in that class. One of them is, I don't know, make noise, right? And then another one is move or movement, right? Not all animals move the same way. Not all animals make the same noise, right? So it makes sense for those to be abstract. And with those methods being abstract, that means that the subclass absolutely has to account for them, right? They have to override those methods, provide their own implementations ideally. But if they don't, and then there's a subclass of that class that does provide an implementation, then that's okay. As long as eventually that method is handled, that abstract method is handled, and there's some implementation of it, then it's all right. And let me repeat that one more time, because I think I might have got my words a bit mixed up. There's three classes. Very top one is abstract. The second one is technically abstract because you have to make it abstract if you don't override some method. The third class that inherits from the second, that class does not necessarily have to override any of the abstract classes or abstract methods, from the grandfather class. So the most abstract one, right? Doesn't have to, so long as the second one has overridden them. And that goes into the idea of talking about a static type versus a dynamic type, what compiles, what doesn't compile. And we'll talk a little bit more about that. I see one question saying a concrete class is derived from a abstract class. I'm not sure I know what you mean by that. I wouldn't say that that's a correct sentence. To say that an abstract class, or to say that a concrete class, is derived always from an abstract class would be wrong. That's not exactly how that works. You can define some sort of abstract class and have no concrete class, extended. That's completely fine, right? So no concrete class. I'm trying to think of an example of it, like in the wild Java API, but nothing comes to mind. But if you want to define some sort of behavior to it, and say, for instance, you just want to use it solely for the purpose of, okay, at this moment in time, I want this object to be viewed as whatever kind of object that is, right? Let's say that it is a child class. So maybe you have animal and you have cat and dog. And then for whatever reason, the dog class is abstract. It's made abstract, right? And it extends from animal. That dog class being abstract does not necessarily mean that you have to have a border collie class that extends dog. But it's perfectly fine and legal to have dog be abstract. There's nothing wrong with that. Hopefully that makes sense. Okay, so final keyword. So a final class cannot be extended. Sort of puts a padlock on the inheritance chain, or rather more of a cement block on the inheritance chain, because there's no way around it unless you remove the final keyword. Trying to think of a use case for this. I mean, it just really, honestly, it's more so just for clarity. If you for certain know that class should not be extended, throw a finally on it. So that way another programmer that comes in is like, hey, I'm going to work on this code base. They realize, okay, well, that one is final, right? So for some reason, maybe it's defined in a comment or two, I can't extend it. A final method can be inherited, but it cannot be overridden, which makes sense, right? It can be inherited, meaning it can be used, but you cannot override the implementation of it. You can't define a new implementation. It's always going to have the same implementation as when it was first created, right? A final variable, which is probably what you're most familiar with, a final variable can be assigned one time. For objects, the reference stays fixed, even if object state changes, right? So all that means is, let's say I have an object of car, right? And inside of this object of car, I have states defined as maybe the brand of the car. I don't know anything about cars. The engine type of the car, the oil type it takes, I think, like synthetic versus whatever. Anyways, let's say you have those things, right? So this is state inside of the class. The reference to that object that is defining car never moves. That does not change. However, the states inside of it 100% can, unless the states inside of that class are named final. Then they can't. But if they're not, it's not like it extends into the box per se, right? To say, okay, well, since this reference is final, everything inside of that box that I'm referencing also has to be final, meaning I can't change it. That's not how that works. Using final or use final when change through inheritance would break concreteness or design. Yeah, exactly. So what I said before. It's more so for design than anything else. And just to make sure, like, it makes sense for you to call that class. You don't want to add you don't want to allow someone to extend, I don't know. You don't want to allow someone to extend a class that defines some pretty important behavior, especially in things like networking, and then have someone just extend it and then add a random method in it that says, I don't know, print out some random garbage into a console, or even print off into the console of some random person's remote computer. Like, that would definitely not be good. So you would certainly want to make that final. So there's use cases for it, right? The sort of overall focus for this, decide whether a class should be abstract, concrete, or final based on its role in the design. I think we pretty much handle that for you pretty concretely on the exam, but that's what you should be thinking. Out in the wild, whenever you're writing programs yourself, think about it. Take a second to sit there and be like, okay, well, what actually makes sense? So that way your structure makes more sense and your code doesn't get bloated too much. Okay. All right, so I got a few questions here. How is an abstract class able to have a constructor? If an abstract class cannot be instantiated, and the purpose of a constructor is to instantiate, why is the abstract class able to have one? So the purpose of a constructor is not necessarily to instantiate. The purpose of a constructor can be a lot of things. The main reason for it is that you are not instantiating the object itself, you're instantiating its state, right? So you're providing some sort of information to its state. Think back to the homeworks where you utilize constructor chaining, right? It wouldn't really make much sense if I can't leverage constructor chaining into an abstract class. That's just kind of bizarre. Like if I define inside of an animal the name, and maybe it's, what's the scientific name for, what is it? I guess it's scientific name, right? Those things are shared amongst all animals. Its normal English name and its scientific name, right? If I can't access that stuff based off of the idea of encapsulation because those variables are private, how else am I going to set it without having a public setter, which you do not always want? If anything, a lot of times you most certainly do not want that, because that means that anyone can set whatever they want for it. So you want to avoid setters and getters at all costs. So of course, they're still going to allow you to have a constructor, mainly for the purpose of you chaining into it, to be able to leverage it being set to something. Hopefully that makes sense. It can still be called by super in its child. Yes. Yep. Exactly. 100%. So final for a variable only applies to the variable pointing to the object as final, but the object itself can be changed. So final for a variable only applies to the variable pointing to the object. Okay, yeah. Yes, yeah. I think it's better to say it. Think of it as reference versus the state inside of that reference. The reference cannot be changed. The reference, the pointer, is final, but the state inside of that reference is not final, or not necessarily final. So you could change it. Okay. Hopefully that makes sense. Oh yeah, a few practice problems to run through. Okay, so first up, why is it legal for an abstract class to contain concrete methods? And by the way, I'm just going to run through these because beforehand we had a little bit of issue with like latency, and we probably still have that because I still have the same crummy old internet. So I'm just going to answer them, and then I'll wait a little bit. You guys can ask questions about it afterwards. Okay, so why is it legal for an abstract class to contain concrete methods? Why is it legal, not illegal? Sorry, had to have some water. So this is because a abstract class is allowed to provide shared implementation in addition to incomplete behavior, right? It can serve as a partial blueprint for the subclasses. So defining some sort of method inside of the abstract class is really powerful, because if you're leveraging that abstract class to its fullest extent, you also have some default implementation inside of it. Not necessarily every single method is going to be abstract. Instead of that being an abstract class, if everything inside of it is abstract, or the vast majority of it is abstract by default, probably would make more sense for you to have an interface, not an abstract class. The thing you can kind of use as a reason for why this makes sense or why this is the way it is abstract. The keyword abstract does not mean that every method has to be abstract, right? It only means the class itself cannot be instantiated directly if it has unfinished behavior, right? So the idea of you having an abstract method, don't think of it as not implemented at all, right? Even though technically it doesn't have a body, it doesn't mean it's not implemented. It means it's like partially there, right? Because it doesn't have a body, which means it really can't be called and utilized because it doesn't define anything. It does not mean that you shouldn't still address it. You absolutely have to address it, as a matter of fact. I'm going to get through these ones first, and then I'll take a look at the chat. So next question here. When would making a method final help prevent bugs? Yeah, this is a pretty solid one. Let's see. I would say when every subclass must use the exact same implementation, and overriding it could break that correctness, that that sort of safety involved, or the required rule set predetermined by the programmer, right? So again, it kind of goes to the idea of, I don't want to allow some subclass to utilize a different implementation, right? I am deeming this method as something you cannot change. You are not allowed to. Idea behind this kind of is like, a final method protects design intent. This is what I said before. It's especially useful for logic, or logic-like validation, or security checks, or like required required output formatting, right? So that would be something that you guys have definitely seen before, wherever you're doing your print statements and things like that. If you have some sort of method that you 100%, you don't want someone messing around with that, right? Well, you want to make it final, because otherwise they can change around whatever's going to be printed out. That's really not helpful. So if a subclass forgets to implement one abstract method, what must be true about that subclass? The subclass has to also be declared abstract, right? You can't get around that. If you don't do that, it straight up will not compile. It just won't work. The sort of reason behind this is like, if the class were to be concrete, it would be fully missing some required behavior, which at least Java does not allow you to do at all. Full stop. Compiler will yell at you. You won't even get to runtime. So yeah. Let's take a look. Oh, okay. All right, cool. No questions so far. Lovely. The code prompt stuff is more so for you. I'm gonna paste these slides, or rather, not paste them. I'll upload them after this, so you guys can go through here and do some of these coding questions. I think they're fairly simple or fairly straightforward, but they're enough for you to, warm yourself up a bit, especially since those of you in Musave's section, your exam is bright and early tomorrow, I believe. So these should be good for you if you want to just quickly run through, be like, okay, I know that, I know this, I know that, I know this. Yeah. I guess one thing I could do is explain, explain whether payroll printer should be final, if every class must print the same legal disclaimer. I must have been writing my resume while I was writing this. But in this case, yes. The reason for it is because making this disclaimer printing method final would just make sense, since they all have to have the same legal disclaimer. That's pretty much it. The thing you're looking for there is same. Making the whole class final is not really necessary. It's only necessary if you also want to forbid some sort of subclass entirely, right? Which isn't the same thing. Instantiate employee directly. Yeah, I'll let you guys do that. Yeah, I'll let you all do that. All right, move on. Oh, there's one question. In regards to the first bullet point, so it is legal because abstract class. Wait, it is. Because. Oh my goodness, why is it doing that? All right. In regards to the first bullet point, so it is legal because abstract class, it can provide a set of shared behaviors, and not all of the methods have to be abstract. Right. Yes. Yeah. It can provide a set of shared behaviors. Yeah, 100%. And some of those behaviors you don't, because when we're defining a behavior, it's not necessarily defining how you go about executing that behavior, right? That's the body of the method. You don't have to do that. But, by that same token, sometimes you do. And if you do want to do that, you just don't add an abstract, at least when it comes to an abstract class, you don't add abstract to the method header. Now you have to add some sort of implementation to it, right? And it can still, and then of course, now we're talking about visibility a bit with, public, default, protected, and private, but I won't get mired down in that minutia. You guys should already know about that kind of stuff. But yeah, pretty much, you're right on the money. Okay, so moving forward. Okay, I think a decent amount of people have issues with this. So hopefully this will help to fix that a bit. Okay, so polymorphism, dynamic binding, hierarchies, and casting. Right, yeah. So this is the cream of the crop, right, when it comes to object-oriented programming. So it's very important. Polymorphism means literally one reference, okay, I thought I had the different sentence there. Polymorphism means one reference type can point to objects of many subclass types, right? The reason, or rather what you can think of with that, is the literal meaning of poly or polymorphism is to have multiple faces or to have multiple forms, right? Meaning you can take on many different shapes, which is very useful for us, but that's literally what's going on. As far as the compiler is concerned, we are able to switch what we appear as from being, a cat, or rather a animal, to a cat, to a dog, and so on, whatever we define as like subclasses. Dynamic binding means an overridden method call is chosen at runtime using the actual object type, right? So, example of that is you can see it over on the right side, where we're talking about dynamic binding, where, okay, we are technically an animal, right, at compile time, because compiler looks at the static type, which an easy way to remember that is on the left-hand side of your equal sign when you're declaring and instantiating something. At compile time, we utilize the static type to make sure that we have some method for it, right? If animal did not have a speak method, not necessarily defined, but it has a speak, if it did not have just a speak method header, it's not going to compile, because we're not guaranteed we have some sort of fallback, right? Then at runtime, we are saying, okay, what's my dynamic type? What am I currently, right? So actively, what is my object type? So that's the actual object type, right? That's the one that's instantiated as. That's the one we're trying to leverage. Sort of animal you can think of as the or the static type you can think of as the backup. This lets code depend on a shared supertype. So yeah, what I just said pretty much. While each object still performs its own version of the method necessarily. If it doesn't have that method inside of dog, it will just de facto to the one inside of animal. A hierarchy is useful only when the is a relationship is real, right? So, or rather, is if it's correct. So the idea behind that is going from cat to animal. Saying a cat is an animal or is a animal is a true statement, right? And it's not even necessarily true, it's just concretely true. But if you go the inverse direction and you say an animal is a cat, that is not always true. That is necessarily true, but because there are cases in which it's not true, you're going to run into issues more than likely. And then, of course, going sideways, saying a dog is a cat or a cat is a dog is just wrong, right? And that's when we get into the idea of sidecasting and things like that. Right, perfect. So upcasting to a superclass is automatic and safe. So what you need to know for that pretty much is that upcasting, that compiles, and that runs. Or rather, you're guaranteed that it's not going to throw a compile error and it's not going to throw a runtime error. It'll work just fine. Downcasting needs an explicit cast. and is safe only when the object really has that subtype. So if you're downcasting into a dog or a cat or something like that, you don't necessarily have certain fields or certain methods. However, because of how it's compiling, the compiler looks strictly at the static type, right? So as long as things line up as far as what you're trying to do to your dynamic type, during compile time, it's going to think of it as the static type, right? So you can get past the compiler perfectly fine, but then once you get to runtime, there may or may not be issues with it, where you'll get some kind of like class cast exception or something along those lines. Fields are resolved by reference type, right? Overridden methods are resolved by the object type. So kind of a good way of remembering this is fields are resolved by reference type, meaning it's resolved by the actual type that you have at why am I blanking on this? At runtime, right? So, and this is talking about the compiler, of course. If we're saying that fields are resolved by the reference type itself, then necessarily you can use different kinds of fields if your reference type matches whatever's inside of that class, right? So, good example of this, if you have dog, and maybe some field that you define inside a dog is, I don't know, breed, maybe. If you have breed defined in there, and you are saying that this is a dog, 100%, you're casting this as a dog, and initially it's an animal, that's fine. That works perfectly fine, right? Because we're utilizing the reference type. Now, if you specifically use the animal as the static type for it, that's not going to work, because we know for certain that there is no field of breed inside of animal because we don't inherit it from animal, right? It's defined inside of dog. The use of instance of to guard a downcast when needed. Yeah, this is sort of the idea of saying or in this case, animal is an instance of dog. Is that necessarily true? Where it's the difference between you can saying like the sort of get class check that we went over with equals and instance of is that instance of goes both ways, right? So if it's a parent or it's a child, either one fits, right? Either one's going to give you a true statement there and say, yep, you're good. That makes sense. I'm good with you utilizing that. A few common mistakes is confusing reference type with object type. Normally what I do is I refer to these as static versus dynamic, just because it's easier to work with, in my opinion. The reference type there is, of course, your dynamic type, and then the object type is your static type. I'm not sure how we refer to them as in the lecture slides, but even easier way of remembering it is looking at that equal sign in the top right, and then saying, okay, on the left side, that's my static type, or rather, that's the type the compiler cares about, right? On the right-hand side, that's the type that runtime cares about. Compiler doesn't really care. Hopefully that makes sense. Assuming every downcast works, yeah. So what I said before about when you're downcasting into something, it's not necessarily going to work. There could be some issues involved depending on certain methods that you're trying to use, and things like that. Forcing inheritance where composition would be cleaner. Yeah, I mean, that's more of the idea of you forcing to have some sort of inheritance relationship when in reality it shouldn't even be its own class. You should just compound them together and then have the same class. That's more class design stuff, but it's important to know. Oh, where's my mouse? Okay, so some practice here, but let me take a look at the chat real quick. Okay, nothing yet. Cool. All right, so to start off with, what prints if x.speak and y.speak are called? Sorry, water break. Okay, so let's just walk through this, right? We have a class animal, right? And it's a default visibility, but that doesn't really matter here. Um, and then we have inside of that class, we have a method void speak, and it is a concrete method as an implementation of system.out.println, and then a question mark, prints out a question mark. Cool. And then we have a dog class and a cat class that both respectively extend animal. And then inside of those classes, we have methods that are overriding the speak method with their own implementations of it. Cool. So what happens if x.speak and y.speak are called? Well, x.speak prints out, what do you call it? Meow. Sorry. X.speak prints out meow, and y.speak prints out wolf, right? The reason for this is the aspect of dynamic binding. You are watching dynamic binding happen with that, because it utilizes the actual object type at runtime, and X refers to a cat object, and Y refers to a dog object. That's, again, the dynamic type versus static type. The actual type we're handling at runtime is the dynamic type. Even though both of them, both the references, are technically typed initially as, or I guess permanently, because they're declared as it, but because they're declared as a animal reference, right? They are technically that. However, again, at runtime, we don't really care about that. At runtime, it's more of, okay, what am I currently? What am I actively right now? And that is the dynamic type, right? Or the actual object type. Okay. What is animal Z equals new dog? A good example, or sorry, Y. Y is animal Z equals new dog, a good example of polymorphism. The reason that that's a good example of polymorphism is because a superclass reference, so in this case animal, is storing a subclass object, in this case dog, which lets one common type work with many specific object kinds, right? So the common type there is animal, and then you could replace dog with any of the subtypes and that would work perfectly fine. Or most times it would work perfectly fine. This is the core idea of polymorphism. You want to write code. You want to write code against the shared type and let the real object supply the behavior. So that's just the idea of, okay, we have a shared type, right? And I'm hosting it on that, right? I'm hosting it on the idea that we're all animals. But the specific behavior is defined in the subtypes of it. The specific behavior is defined in dog. The specific behavior is defined in cat, in cow, fox, whatever. That's sort of the whole point of it. Which cast is safe? So explicitly casting X to be a dog, or explicitly casting Y to be a dog. Well, I feel this is kind of self-evident, but so the explicit casting of Y into a dog, perfectly safe, right? Completely fine. Y literally references a dog at runtime anyways, so that is perfectly fine. And that would actually, by the way, this is the idea of you having or rather, I guess X is the sort of class cast exception. Is the class cast exception example. And also X is the interesting case. Y is not so much. Y, I feel like you can kind of infer, yeah, if you cast it into a dog, I mean, it's actively a dog, so that'll be fine. It's actively a dog at runtime. So X actually refers to a cat, right? So what its actual type is being a cat. So casting it to a dog would cause a class cast exception, because that's side casting. Side casting is like immediate no.
It's just not going to work. 100% does not work because of how Java handles inheritance. You have a method that accepts a shape parameter and calls area. Explain why this design is more flexible than separate methods for a circle, rectangle, and triangle. I'll leave that for you guys to do. Describe one case where a hierarchy is a poor fit and composition would be better. Again, I'll leave that for you. Those ones on the right, you maybe don't worry about those too much. Work on the difference between polymorphism and, or no, sorry, not the difference between polymorphism. Work on the difference between upcasting, downcasting, sidecasting, and understanding truly what is polymorphism and understanding why it's important that we have dynamic binding. Let's take a look. What will happen if I write dog z equals new animal z dot speak? Okay, so first thing, right, is you're saying that at compile time you are a dog, right? If you're saying that your type at compile time is of a dog, then dog has a method speak, right? So that'll work perfectly fine during compile time. It'll compile just fine. Did I say eat? I meant speak. It'll compile just fine, right? Once we get to runtime, because animal has its own implementation of speak, this will compile and run perfectly fine, right? And what will actually print out is question mark. It won't be wolf, or sorry, no, did you say dog? Yeah. It won't be wolf, right? It'll be question mark. The reason for this is because we look at the reference type, and the reference type is also what we call the dynamic type, pardon me. The dynamic type is what we also call the actual type. So the type that we're handling during running. Type that we're handling while running, in this case, off your example, is animal. So we look inside of the animal class, we look for the method that you are utilizing, which is speak, and we say, okay, do I have it? And we do, we have it. We confirm that at compile time, right? At compile time, dog has it, so cool, that's probably fine. And then we go up and we say, okay, does animal have it? Yes, it does. So now I'm going to print out question mark. That would work just fine. And it would use animals. It would use animal speak method. Hopefully that makes sense. Okay. All right. Okay, so moving forward, let's talk a bit about interfaces and the comparable interface, which you guys should have used at this point, I hope. Okay. So, an interface defines behavior that classes promise or guarantee to override or to provide. It supports polymorphism without forcing a shared superclass implementation. A class may implement multiple interfaces, which is a major design advantage. So being able to essentially satisfy multiple contracts at once. You use interfaces for capabilities such as comparable, iterable, or more custom behaviors like drivable, so writing up your own interfaces. So the comparable interface is comparable gives a natural ordering through compare to. So it literally breaks it down into basic numbers for you, pretty much. Or rather, it leaves that for you to do, but that's why it returns an int. Right? It returns some type that is numerical that you can kind of leverage and say, oh, okay, so this one's bigger than this one by some metric that you define, or it's equal to it because they zero out. Compare to returns a negative value, and this is what it should, but it should return a negative value, 0, or a positive value. Technically, you could have like specifically -1, specifically +1, and then of course 0. The problem with that is it kind of rips a lot of the information or useful information away from you. If you don't know exactly how big something is, that's not always necessarily a problem, but it definitely pulls things away from you, right? It is more advantageous to you to utilize the idea of just, like, let's say, for instance, you have two strings that represent the names of different objects, and you want to know whose name is longer, or you want to know, I don't know, you want to know whose name is longer, right? You can do that easily by just doing the math behind the scene and saying, okay, if this one's bigger than this one, give me a -1. If this one's bigger than this one, give me a 1. If they're equal, give me a 0. Or you can say, actually, here is a negative number, a positive number, or 0, and now I know exactly how long the difference is, right? I know how big of a difference there is, which you can definitely leverage in other methods. Sorting algorithms can compare objects through compare to instead of knowing class-specific details, right? So that's another example of encapsulation, pulling things away from you, or pulling things away from the user, rather. The sign matters more than the exact number that is returned. Right, exactly. So then all in all, for compare to, make sure you return a negative value, 0, or a positive value. Okay, I see question here. But why can an animal be considered a dog if it may not be a dog? Hope someone answer them. Let's see. The compiler does not know the object's actual type of compile time, correct? It gives the programmer the benefit of the doubt and lets the line compile. When the JVM actually tries to run it, it recognizes that it isn't a dog and doesn't run that line of code. Wait, for which one? If you're talking about the line that the person utilized to, like, say, hey, what will happen if I write this? An animal can be considered a dog if it. I'm not sure if you're referring to the one from before. Because if you're referring to the one from before, then yeah, absolutely. But if you're referring to the one where you're talking about dog z equals new animal, that's a little off. But so basically the idea, you got most of it right though. The compiler does not know the object's actual type at compile time, which is your dynamic type, right? So essentially think of it as it's going down a checklist. It doesn't get too involved on the level of saying, oh, this is 100% going to be this, right? I'm not guaranteeing you that. And frankly, there's not really a way of guaranteeing that. So as one us the poor, yeah. As that person put it, it is pretty much giving the programmer the benefit of the doubt and just allows the line to compile, because it's like, okay, well, we know that inside of the class that is the static type, you have evidence of that method, right? So in that case, with speaks, you have that method. That's in there, 100%, right? And then we say the JVM actually tries to run it. It recognizes that it isn't a dog and doesn't run that line of code. Not necessarily. It will look at it and say, okay, this is an animal currently, right? At the actual time, it is an animal. That's fine, as long as inside of that dynamic type, the method is there and it has an implementation, that will be okay. It will run. That's perfectly fine. Okay, hopefully that's clear. Okay, so a little bit of practice for this. Okay, sorry. Okay. Okay, so to start off with, why might a class implement an interface even if it already extends another class? Well, this is because Java allows only one superclass, right? So you can only extend from one thing, but a class can implement multiple different interfaces all at once. That is perfectly okay. The reason for this was kind of said before, but just to reiterate, interfaces let a class guarantee or promise to provide extra behavior without changing its main inheritance hierarchy. Okay, so what does compare to return when two objects are equal in ordering? Yeah, I mean, it returns 0. The reason for that is just because of how compare to works, where it is a subtraction problem in essence, pretty much, right? It just compares the state of things and then subtracts it down into a certain number, and then if everything's equal, it would obviously relate to 0. And then I guess a good way to remember this, because I think some people have issue with like, hey, how do I actually read compare to? Because sometimes you can get it mixed up, where if you have one object compared to another object and you don't know what that compare to method looks like, you should be able to know, like, okay, I'm giving you two objects, I'm using compare to, it returns a negative number, which one of these is bigger, right? You should be able to answer that question based off the idea of this is how the contract kind of works within compare to. Negative means less than. 0 means equal, and positive means greater than. The way that you can look at that is literally take compare to the method, replace it with a subtraction sign, and then subtract the states. And in that case, if the one on the left is bigger, right, that'll be a positive number. If the one on the right is bigger, that will be a negative number. That's how you know it. Why can a sorting method work on, why can a sorting method write, wow, my bad. I can't read. Why can a sorting method work on many object types if they all implement comparable? This is really just because the sorting algorithm only really needs compare to, not any class specific details, right? It just needs the compare to method, and that's all for it to work. The algorithm itself becomes reusable across many different data types, as long as each type defines how two objects should be compared, right? So that, again, that's the usage of the comparable interface, saying like, hey, this is how we should be compared, right? Compared to, so books are ordered by price from low to high. Then describe how to break ties using title. Yeah, I'll leave that for you all to do. I'll leave that all for you to do. Hold on. Wait a minute. Hold on. Wait a minute. Hold on. No, my bad. Hold on. I just realized something. Let me see. I think I misspoke massively. I did. Sorry about that. Yeah, for the dog z equals new animal. Yeah, no, that won't compile. My bad. Yeah, definitely my bad there. That goes back to the idea of, and the person before won us the poor. Yeah, my bad. You are fully correct there. It recognizes that it isn't a dog. Yeah, 100%. Yep, my mistake there. The reason it doesn't utilize it is because of the is a relationship, which then someone said eagle e equals yes, that is why. Yep, 100%. That is why. A sort of a bit more on that. When you say that animal A equals new dog, we are already guaranteed that dog is necessarily an animal because we can utilize just the idea of saying dog, the actual type, is A, and then the declared type. If that sentence makes sense, then it will compile, it will work. right? So it's going to function correctly, right? If you did, and by which I mean it won't compile, sorry. If you were to do, or it would compile, geez, I am so sorry. I am exhausted. If you did animal A equals new dog, a good way of knowing if that's 100% going to compile or not is if you do take the one on the right, your dynamic type, and then write is A, and then write the static type name. If that sentence makes sense, it's going to compile. If it doesn't make sense, or it is not always necessarily true, it will not compile. So in this case, you saying dog Z equals new animal, taking animal and then saying is A dog. That is not always necessarily true, so it will not compile. I believe the error that you are given for it provides you I want to say it's a mismatch error. I think it gives you a mismatch error, or it says something to the effect of incompatible types. Yeah, sorry about that. Yeah, hopefully that clears it up. That's definitely my bad. Okay, yeah, super sorry about that. I was sitting there thinking, like, that person's explanation makes perfect sense. Why am I saying that's wrong? And then I realized that I'm wrong. So again, super sorry about that. Okay. I'll leave this code portion for you all to do as an exercise. And I'll just move forward into ArrayList and generics. Okay, so in this one, I'll kind of go through a bit quick because you guys should have a lot of experience with this at this point. So collections themselves, so list is an ADT, store many values. Generics preserve type safety and reduce casting involved. So ArrayList stores element in a resizable array, right? It has a backing array, it resizes it dynamically. You don't have to worry about that when you're using it. Fast index access with get and set. So that's just talking about Big O. When we're talking about getting and setting something inside of an array list, it's very quick. Insertions or removals near the front can be costly because elements shift, right? Because the reason you can think about this is because it's a backing array, right? Literally, when you are adding something into an array, if you want to preserve all the information, the only way for you to do it is you have to shift everything else down. And there's no real convenient way of doing that. It's going to be kind of irksome to shift everything down, especially if you end up having like 1,000 different elements, right? And you want to add something specifically at index 1. That's going to be painful. So a few common methods that you guys have all used is add, get, set, remove, size, and contains. Size there kind of just as like a catch. A lot of people get them mixed up. Realize that for arrays, we have .length, right? And with .length, it is a variable, right? It's not a method. You just put .length, done. Inside of an array list, it's not length, and it's not a variable. It's a method. So you do .size parentheses, that gives you the length of the backing array. Primitive types must use wrapper classes such as integer, right? And the reason for this is because ArrayList utilizes generics. Generics do not take in primitives, they take in reference types. So ArrayList with string as its generic type means the list is meant solely for string objects. This gives compile time checks and avoids unsafe casts later on. It also makes it so you don't have to write multiple different classes all defining the same stuff, but with slight differences based off the fact that it's not a string that you're handling, it's a integer, right? Type parameters make classes and methods reusable across many data types. Yeah, so pretty much what I just said. So a good way to remember the sort of cost idea is when you're getting an element, typically it's O of 1. Sometimes, trying to think of a case where it wouldn't be O of 1. Yeah, actually, I don't know. Just think of it as O of 1. Getting some sort of element, that's where it's powerful. is grabbing information. Getting information is like almost entirely, if not entirely, O of 1, meaning it is super quick, right? Now, adding to the end of a list, adding to the end is also usually O of 1. The only time it's not O of 1 is when we then are out of space, right? So if we get to an array list and let's say the size is 10 and we have 9 elements, right? We have 9 elements, we add one more to it, that's fine. If we had 10 elements, we add one more to it, can't do that. You have to resize it, meaning in the back end, you have to create a brand new array, brand new array, and then iterate over one other array, the original array, and import everything. Say this, at this index, this number goes. At this index, this number goes, da-da-da-da-da, all the way down, right? Which is, bad. But that's the only case. So normally, O of 1. Now, inserting at the front is O of n, 100%. Because there, in that case, the only time that's not O of n is like the very specific case where you have no elements. If you have no elements, it's completely empty, it's O of 1, right? Because it's immediate. But if it's not no elements, it could have n elements, right? And if you have n elements, that means you have to shift down n times. So it would be O of n. Okay, so what values remain? Where's my mouse? There it is. What values remain in nums? So the array list nums after the code runs. Okay, well, this is fairly straightforward, right? So for problems like these, if we ask you this on the exam, write it out. It'll be more complicated than this, but write it out. It's very helpful to keep track of stuff. So the answer here, or I guess just to walk through it, we have nums is empty. Then we add 4 to nums. So in the index 0 of the backing array, it's 4, right? Add 1 to it. Index 1 of the backing array is 1. Index 2 of the backing array is 7. So we have 4, 1, 7. And then nums.remove 1, we remove the value 1, but importantly here, the 7 shifts down to the left. So what you actually get is an array containing 4 in index 0 and 7 in index 1, right? There's no null entries. That's another thing about array lists. You will not have null entries. It's going to get rid of those for you, right? It's smart enough to shift everything down towards the front of the list. Okay. Which call removes by index here? Which call removes by index here, and why? Remove 1. So in that case, remove 1 removes by technically it could remove by the index, or it would remove by the actual data type. Actually, no. This is a good question. Removes 1. 1 in this case is an int, right? It's not an integer. So it wouldn't remove the element 1. It would remove at the index 1. Ooh, that's a good question. That one might be on the exam. So to repeat that, notice that with the remove method, you can remove at an index, or you can remove by the data type, right? So it'll search through the list. It'll say, okay, this is the data type that I'm matching. I'll remove that. But 4, 1, 7 in this case are integers. They're not ints, right? So they're not primitives. So when you do nums.remove just 1, that's removing at an int. Does not match the data type. So it's going to say, okay, well, obviously we're talking about a index here. So I'll remove at that index. Hopefully that makes sense. And the way that you could fix this is by casting that 1 into an integer. And then it will remove the value 1, not at index 1. It just happens to be at index 1. Okay, so what is the difference between capacity growth and the logical size? Logical size is more how many elements are currently stored. Capacity is more of how much the underlying array structure, space is available before resizing is required. So capacity, how much can we actually have? And then the size is how much do we currently have? Again, I'll leave the right and the recent stuff for you all to tackle. Okay, let me take a look. Oops. Okay. Can you explain bullet point 2? You're saying, wait, hold on, let me see. You're saying it removes data type first, and if the passed in value doesn't match the data type, it defaults. So no, it's hold on. So what's happening there is it doesn't even check for that, right? It just says, think about the idea of overloading, right? So in this case, in the array list ADT, you have, I want to say you have 3 removes, but I know for certain you have 2. So let's say you have 2. You have 2 removes. One of them is remove at index, basically, and then the other one is remove at element, but it's just called remove. So one of them takes in a value of int. The other one takes in a generic type matching the one that is currently being used by your array list instance, right? So it will scan and say, okay, which remove am I looking for? And in this case, because it's an int, it matches that method signature. It goes into that remove, which is at an index, and removes at that index. It's not looking for that element. So if we were to switch the value of 1 and 7, we would have 4, 7, 1, right? Now, if you have 4, 7, 1, nums.remove 1 is completely different and will result in a different result than nums.remove cast integer 1. Those would be 2 different results. If you did nums.remove 1 with the structure having 4, 7, 1 in sequence, you'll result in 4, 1, not 4, 7. And the reason for that is because we're removing at an index because it is an int. If it is the generic type matching what generic type we're currently using in our array list instance, which is integer, the resulting structure would actually be 4, 7. It would remove the value that is matching it. Hopefully that makes sense. Okay. All right. So a little over asymptotics. Yeah. So, how does Big O work, right? When we're reading a Big O expression, more often than not, we want to remove, we want to remove constants and low order terms. What that means is we want to find the thing that grows the largest. So for an example, we have 3 times n plus 5. Well, in this case, the constant term is 5. That doesn't really change much because we're approaching infinity normally with these cases, or that's what we're looking at for like worst case. So we remove 5, and now we're left with big O of 3n. Well, 3 times n, that's like saying 3 times infinity. It doesn't really matter that much, right? So it's still infinity. So we remove 3 entirely. And so now we're left with n. So it would just become big O of n. Nested loops often multiply, so that's where you get n times n, stuff like that. 2 full loops over n items often gives big O of n squared. I imagine you've seen that. Actually, you've had a homework over this, so yeah, you've definitely seen it. The sorting algorithms are a good example of this, the ones we've covered so far, with the exception of merge sort. They don't have to be like for loops, by the way. They can be for loops, while loops, do while loops as well. It's just the idea of constantly, and they can be recursive as well. It's the idea of sort of you iterating n times or you going through something n times and you're not halving the size at any point, you're not doing anything really to lessen your amount. And you have to lessen it by a sizable amount. Mert sort is a good example of that, where it's in log n, and the reason it's log n is because we have log n levels that we're going through for merging things back together. Because it's recursive in nature, it's splitting things 2 by 2 by 2 by 2, right? Which would technically speaking divide by 2 for n, which would result in roughly log n. Sequential blocks usually add, then the dominant term wins. So that's the idea of not having things nested together. So if you have a for loop and then outside of that for loop you have another for loop, that's like the idea of what, depending on the term that you're, iterating through. But if we're iterating by n in both of them, that would be the equivalent of having big O of n plus n, right? And in that case, you just pick the dominating term. Both of them technically are the dominating term, so you just take one of them. So it would be big O of n. Best, worst, and average cases may differ. So you have to be purposeful about which one you're referring to. For this class, we really only care about worst case. Actually, I think we only care about worst case. So just know the worst cases of these algorithms. Common orders of growth. So big O of 1 is direct or direct access, or like really, really, really simple arithmetic that's almost instantaneous. For login, binary search style halving, yeah, just pay attention to halving. When we look at login, more often than not, we're talking about halving things. That doesn't necessarily have to look like divide by 2 or something like that. That could be modding by something, utilizing modulus. You can oftentimes end up splitting down a structure well enough that it cuts off roughly half the time that it takes to run it. But pay attention to the idea of just having things. Big O of n is just a single pass through the data, but a complete pass through of it. So you are guaranteed every time that you use this, normally worst case, you're guaranteed that it's going to iterate through every single element, right? Which is linear time. Big O of n log n is normally like as best, is normally as worse as we want it when we're actually using these algorithms. Big O of n squared is pretty bad. Like that's bad. And those are double loops normally. Oh, and then also to be clear, if you have two different lists, each of them, we can say are, let's say one of them is of length n, one of them is of length m, right? The big O there would be big O of n times m if they're nested. It would not be big O of n squared or something like that, because n and m could have varying lengths, right? So it would be big O of n times m, depending on the length names. So choose the simplest dominant term that still describes the scaling right. So that's just the idea of, if you had like 36 times n and I don't know, plus 470 times n squared, technically speaking, 470 times n squared is your dominating term, but you can get rid of 470 because, again, it's 470 times infinity, right? So it would just be n squared. Oh, wait, what was it? Oh, I guess, did I know? No, I didn't. Okay. That's fine. Let's see. What did you say here? For long I equals 0, I less than big ass number. I plus plus for long, is it O of 1 or O of n squared? I'm assuming that those loops are nested. Yeah, I'm assuming those loops are nested. It doesn't use n, so I guess O of 1, if the 1 millions or whatever were in, it would be correct. Yeah. When you see a constant number like that, no matter how big you make that number, well, unless you make it like really, really big, it's going to be O of 1. And I think even if it's a super, super big constant number, it's still considered O of 1 because you know how big it is, right? when we say in is arbitrary, by the way. Like that can be the name of something. Like in of itself is a replacer for you saying the array length was this, or the list length is this, right? Or the number of data points that could go infinitely or semi-infinitely. Yeah, so you're right. Hello, a bunch of numbers. You're right. It doesn't utilize, not necessarily in, but it doesn't utilize something that we don't know 100% what that term is. So it would be O of 1. Or sorry, it does use, my bad. It does use a term that we 100% know what it is, which is in this case is 1 million, I guess. So we know it's going to run 1 million times. That's O of 1. It's constant time. Now, if you replace that with n for both, it would be O of n squared. If you replaced it with, I don't know, k, right? And k is defined as the length of something. Then that would be a big O of k squared if they're nested. Hopefully that makes sense. Okay. Where's my mouse? Okay. All right. So asymptotics, a little bit of practice for this. All right. Determine the big O for each loop block. Okay. So the first one. First one is a loop and a inner loop. Both of them, their upper bounds are n for each of them, right? And it looks like the way we're incrementing / decrementing is incrementing by 1 each time, right? This one's pretty simple. This is just big O of n squared, 100%. The reason for it is because the outer loop runs n times, and the inner loop also runs n times for each outer iteration. So the work multiplies. Yeah. So for the second one, we have a loop that is k equals n, so some large number. K while while k is greater than 1, divide k by 2 for every iteration. Okay, well that one is halving. That looks like halving to me. So every single iteration we're halving. That sounds like big O of log n to me. Each iteration cuts k, the value of k, in half. So the number of steps is the number of times you can divide n by 2 before reaching 1, or dividing k by 2 before reaching 1. Okay. I feel like those are fairly straightforward. Just pay attention to your bounds more than anything else. If your bound is, I less than a concrete number, like even if it's 1 billion, and then your inner loop is by n, technically that's 1 billion or whatever times n. So it would just be big O of n. We could probably get you with that. So, be careful with that. If these blocks run one after the other, what overall order remains? It's just big O of n squared plus log n, which in that case, the big O of that as a whole would just be n squared. That's it, because it's the dominating term. Explain why. I'll leave the rest of those for you all to do. They're not too bad. Mostly just conceptual stuff. Okay. No new questions? Cool. Okay, so now into searching, which I don't think we have too much left to go. I'm pretty sure. So stick in there, hold in there. Not too much left. Okay, so searching. We have 2, I think. I think you guys have 2 searches, linear and binary, pretty sure. So linear search, checks elements one by one until the target is found or the structure ends. This works on unsorted data. It's worst case time or time complexity is big O of n. So worst case is it has to go through the entire structure. Simple and reliable for small or unsorted collections. Yeah, so linear search is good if you just want, I don't know, like if you have concrete length, where the length of itself is like, I know that I have 20 things. I have 20 items, right? Linear search is way easier to use than binary search. And at that point, it makes a lot more sense. Because it's less computationally expensive. Sorry. So binary search requires sorted data. It has to be sorted. If it is not sorted, it does not work. And random access to the middle. So it can access the middle, basically. Discard half of the remaining range after each comparison, meaning if the middle number or whatever item it is easy. If the middle item is bigger than whatever your target is, then you cut off the right hand side of it, or left hand, depending on how it's sorted. But normally it's sorted from like least to greatest. So if we're assuming it's least to greatest, cut off the greatest side, which would be the right hand side, and then do the same process over and over again until either 1, you find your item, or 2, you run out of array, basically, or you run out of list, run out of the structured space because you've cut everything off. The worst case time here is O of log n, which should make sense because, again, it's the idea of just halving. If the data is not sorted first, binary search is not valid, right? So it just doesn't work. Binary search repeatedly checks the middle, then keeps only the half that can still contain the target. So what I basically just said. I think that something important to know here is if we ask you like how many iterations or how many checks do you do until you find some item, notice that the first thing you do is check, right? So if you check and you then are like, oh, well, this item is bigger, right, than what I'm wanting, then you half. After that half, first thing you do is check. Then you half, then you check, then you half, then you check. That's the loop there. So if you're halving 4 times, you've checked 3 times. Or sorry, no, my bad. If you're halving 4 times, you've checked 5, right? If you've ended up in a situation where you've gotten your item, you always have one more check, basically. So let's say you find it immediately, right? If you find it immediately, that means that you had no splits. So you found it immediately, which means you had to check 1 time, right? If you have to split once, that means you checked it first. Oh, it's not it. Half it. Check it again. Oh, it's there. Cool. Don't have to half again. It's 1 half, 2 checks. It's just a little. It's almost like a one off by off by 1 error. So I would be shocked if we didn't ask you a problem like tracing something like that on the exam. On both exams for Chambers and MooSafe. So just know a good way to remember it is tracking it through, tracing it, and saying, okay, I have the array, the list by 6 times, right? You did it 6 times, and then you did find something in the end, you checked 7 times, 100%. Guaranteed you checked 7 times. Okay. 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 Let me check the. Excuse me. Good Lord. Let me check the chat. Okay. Nothing new. Cool. All right. Okay. So, all right. So I guess I'll just go through these. Linear search. Give one reason linear search may still be the right choice, even though it is slower in the worst case than binary search. Well, for that one, I mean, well, I guess 2 things, technically. One, which seems a bit more obvious, I think, is if you have unsorted data. If it's unsorted, it may actually be worse for you to sort it first and then do a binary search than it would be to just do a linear search, right? So, excuse me, good Lord. So if there's unsorted data, you can't use binary search. You have to use linear search or some other kind of search that you don't know yet. Another example of it is, and it's a little bit out of the scope of the class, but it's still important, is if you have a small set of something. Like if you have 30 items, it's finite, right? And you know the length of it. If it's 30 items, use linear search. Computationally, it is far less expensive than binary search. Binary search uses something like division. Division is computationally expensive. You don't want to just use that. If you can, if you have something really small, you want to use something that may necessarily take longer in the long run, but it just requires less structure to it. So linear search would make more sense when you have less data, but overall, for our purposes in this course, it's mainly when the data is unsorted that linear search is king over binary search. How many elements might linear search inspect in the worst case for n items? Well, we just said this, right? N elements. This happens when the target is either the last thing that you check in the structure, or it's just not there, right? If it's not there, I mean, you don't stop halfway through, right? You still have more things to check. You go to the very end of the whole thing, and then you get returned either like false if it's not there and you don't get the item, or you just get null, right? So yeah, so n elements. So binary search steps, so we have array 3, 8, 11, 19. Oh, good Lord, excuse me. 3, 8, 11, 19, 24, 31, 42. Show the low, high, and mid positions while searching for 24. Okay, I mean, I think I can reason this out in my head. So actually, no, you guys do that. I'll leave that for you. That's not too hard. That's good. That's a good thing to have for the sake of writing an implementation of it. But normally, when you're doing it in your head, you're not even really thinking about that, right? You're just like, okay, go halfway, right? And in this case, we have 1, 2, 3, 4, 5, 6, 7 elements, right? It's odd elements, so that's even easier. We go to the fourth spot, third index. That's the number we're checking first. Now, if it's even, normally you go to the left. So let's say we have 3, 8, 11, 13, 19, 24, 31, 42. The two middle numbers now are 13 and 19, right? Just pick the left one. It's arbitrary. You just kind of do whatever. But normally, at least I think in this class, we pick the left one first if it's odd. You don't average them. Don't average them. I remember I saw one person do that. That is extremely wrong. Don't do that. Okay. Can binary search be used on an unsorted linked list? I mean, no, because it's unsorted. Binary search requires sorted data, and oh, that's important too. I don't know if we'd go this in depth. We might. So it's good to know. It's unsorted, right? Obviously, but also within a linked list, remember that it does not have efficient middle access at all, right? It's actually pretty bad. So an unsorted linked list has neither of those properties. So it doesn't just not have sorted data, it's also middle accessing is bad. So it wouldn't work. Or it would work, it would just be really inefficient. What must be true before binary search starts? Data must be sorted, right? The half discarding logic is no longer valid, basically, if it's not sorted. Okay. Yes. Okay. Well, let me take a look. Oh, okay. There's someone here. So if a question is asking how many iterations of binary search to get to etc., the iterations would be the number of checks or the number of halves. We would be specific about like if it's the number of checks or the number of halves. But the number of iterations is the number of times that you are going through the full process. So I would say that the number of iterations is when you've done your the number of times you've done your halving, not your checks. I think that we would be more specific about that because that is a bit confusing. But full iterations, the way I would define it, is by the halving process, because that happens after you check. Hopefully that makes sense. I think we'll be specific about checks versus halves. I don't think we'll just say straight up iterations. Now for bubble sort, or search sort and selection sort, yeah, we'll use iterations. We'll say iterations. We won't say number of checks. Hopefully that clears that up a bit. If you want as well, you can ask on Ed and get more of a TA consensus there. But to my knowledge, we'll be specific about it either being the number of checks or the number of halves. But if it is iterations, my strongest assumption would be that it is the number of times you fully go through halving and moving around your low, your high, and your mid variables and all that. So that would equate to your halving. Okay. All right. Sorting with polymorphism, that's just fancy terminology for basically just utilizing compare to. Selection, bubble, and insertion. Memorize these. Not the full implementations, but memorize the worst cases. They're pretty obvious. But selection sort, the core idea is that you find the smallest remaining item and you swap it into place, right? What you notice there is a few swaps. It does a few swaps and it still scans the unsorted tail each pass. So then for bubble sort, you do repeatedly, you repeatedly swap adjacent out of order pairs, and you kind of bubble them up or bubble them down. I guess it depends. But I think that normally the most convenient way of doing it, or the most used way of doing it, is bubbling things up to the right. Oh, well, there you go. Yeah. Largest items drift right each pass, right? So you're bubbling something up to the top. So almost like something bubbling up to the surface of the water or something like that, which would be big O of n squared. Insertion sort is inserting each new item into the sorted left side of the array. So you almost like make a pseudo array inside of your list or whatever that is sorted, that I'm like guaranteeing it is sorted, right? It's really good on nearly sorted inputs. So if it's nearly sorted, you basically get the number of moves is the number of iterations. Sorry, that sounded so dumb. The number of items that are out of place is pretty much exactly how many iterations you need, and then you're done. So a sorting method written for comparable can sort students, books, or any class that provides compare to. I'm so sorry. I don't know why I'm yawning so much. Yeah. So all that's basically saying, I mean, any of these sorting algorithms in the real world, you want to have some sort of contract defined there for compare to or the equivalent of compare to, right? Because utilizing just selection, bubble, insertion on numbers alone is just dumb. Like, that's not what you're doing. You're going to use it on actionable items that define multiple different states, right? So sorting cars or sorting people. People are not just a number. Well, I guess to some governments they are. But in reality, they're not just numbers, right? They have a name, they have a height, they have a body weight, they have a job that they have, things like that. The only way that you're going to be able to compare those effectively and meaningfully is with the compare to method. Okay, hopefully that makes sense. There we go. Okay, yeah. Okay, all right. Merge, sort, and recursion. Yeah, recursion is a beast for a lot of people. So, can you go over ascending and descending for sorting? What do you mean? Like an example, or because ascending and descending for sorting. Normally, when we refer to that, we're referring from left to right. Like we say left side for ascending, smallest, and then left side for descending, biggest. I'm assuming that's not what you meant, but I'll go over merge sort and recursion and then the practice, and then I can go back if that is what you meant with an example. Okay. All right. Okay, so merge sort is big O of n log n. And yeah, I think the important thing here, more important, is knowing recursion and knowing how to be recursive. So I'll be specific on that. So, to start off with, a recursive method solves some problem by calling upon itself on a smaller input, right? So it breaks down the problem, basically. Every correct recursive design needs a base case that stops, right? The base case is the simplest case you can possibly have for that problem, right? Very common examples of this are factorial, right? Factorial, the simplest case there is factorial of 0 and factorial of 1. The reason for this is because it is a single number, right? And there's nothing really involved with it. It just returns it, right? Factorial of 0 returns a 1, and you're done. Factorial of 1 returns a 1, and you're done, right? Now, factorial of 2 and above technically returns a string of terms that you're multiplying together to receive the result, right? So you can do that recursively. Trace recursive calls like a stack. Call down, then return back up. Yeah, that is how you should be tracing any recursive problem. As soon as you see it calling itself, mark that and say, okay, let's say it's the name of the method is recursive method, right? Or something really simple like that. If you're calling recursive method in recursive method, that is an entirely different call. And normally inside of the actual call itself, that's where we're making that update to whatever the input is. For factorial, when we are updating it, we have changed things into, actually, no, I won't even use that. I'll use merge sort because we have it right here. So I guess we'll go over the flow of merge sort really quickly. The way merge sort works is it splits the array into two halves, keeps doing that, and it recursively sorts the left and right half. And then it merges the two sorted halves into one sorted result. The tree has about log n levels. Each level does O of n total merge work. So the overall time is O of n log n. So I think I mentioned that before, where the actual like depth is log n. And then the work of merging everything is the n. That's where that comes from. So for the sake of recursion, we do merge sort of A. In this case, I suppose we're assuming the A is the array. A good base case is whenever the length of that array is either 1 or it is 0, right? Meaning it's already sorted. I mean, just by nature, right? We are guaranteed that's sorted because it either has one element in it or it has 0 elements in it. And if it has 0 elements in it, it's sorted because there's nothing there. And then if you have one element, there's nothing to compare it to, right? So it's just sorted automatically. So that's what you check. That's your base case. Then you split into left and right. So in this case, A is an array, let's say it has 4 elements. You split it into a left and right section. Left section is the first 2 elements. Right section is the rightmost 2 elements, which is just the last 2. And then you call merge sort on that left half, merge sort on the right half. You keep doing that until you get to your length less than or equal to 1. But notice that every single time merge sort is called, we're calling into a merge algorithm that takes the left half, the right half in the main array. I won't go into exactly what's going on inside of merge because you frankly don't need to know about it. Just know that it merges. So at each merge sort call, there is a merging operation happening there. That's why it happens on that level, right? Yeah, hopefully that makes sense. But to actually trace this out, write down every single time you are making a call. You write it down. It's its own individual block that you are pushing down on the stack. and you write it out. And a good idea for this is to write out like the number or what the input is at that current time. So say, for instance, for merge sort, if you're calling merge sort over and over and over again, it can get confusing and you can lose track of things really quickly, right? Even if you're writing down the calls. So if you write down the calls and you list inside of the box that represents those calls, maybe the length of the left array at that point in time, the length of the right array at that point in time, doing that. And then what you'll end up with, for merge sort especially, is you'll end up with essentially a tree. I mean, you'll end up with a full-on tree. With factorial, on the other hand, what you would end up with is, like let's say you did factorial of 4, you would end up with the first call, which is factorial 4, the second call, which is factorial 3, then factorial 2, then factorial 1, and then it returns. What that looks like is it's pushing down on a stack. So the very first thing on your stack is factorial 4. Above it is 3. Then above that is 2. Above that one is 1. And then once we've hit the base case, we return. And the way you can visualize that is returning, pulling off the stack, factorial of 1. Factorial of 1 returns you some number. It returns you 1 specifically, but it returns some number, right? So take that number out, and then you know that you're multiplying things together. So take that number out, write it down, write multiply, or write times, right? And then return the next method call, write that number down. Next method call, write that number down, and so on. And multiply that together, that's your number, right? And you can follow that same idea depending on what's happening at the call site and within that method. Okay. Should we remember the implementation for every sort? I think for Chambers and MooSave, it's a bit different. So I don't want to say one thing concretely for both of all of you. However, for MooSave, if I were you, pick your favorite sort and yes, memorize it. That I think that would help you. If don't memorize all of them, I think that would be a bad idea. I mean, you can do it, but I think that's kind of wasting time. Memorizing things in the first place is kind of a waste of your time for the most part because you don't really understand what's going on. But if you particularly are decent or good at implementing selection sort, beat it into your head. If you're MooSave, beat it into your head. Chambers, on the other hand, if I were you, focus on understanding the algorithm and understanding tracing, understanding how to use it, understanding that more so than writing it. But yeah, and take that with a grain of salt as well, because I can't, confirm or deny whether it's going to be on the exam and not going to be on the exam. I can't do that for you. But if I were you, if you are in MooSave section, I would definitely pick your favorite sorting algorithm and beat it into your head. Don't forget about the other sorting algorithms, though. That would also not be good. Be aware of them, but pick your favorite one. Make sure it's, deeply ingrained in your mind. For Chambers, on the other hand, be aware of the sorting algorithms, know how to use them, know how to trace them, all that stuff. But I don't think you need to pick one to fully memorize it. Okay, cool. Let's see, how many more? Oh yeah. We're almost there. Okay, so a little bit of practice for sorting and recursion. Run one full pass of selection sort on 6382. What array remains after the first swap? So when we are utilizing insertion sort, right, we sort of immediately for this stuff is just know the difference, right? I think that's fairly straightforward, but still, don't get them mixed up. The first thing that's going to happen here, right, is for selection sort, we find the smallest element in the array, right? That's what we're doing. We find the smallest element in the array, which is 2. And selection sort simply swaps it into the first index on the first pass. That's it. That's all it does. And we're done. That's it. Really straightforward. But notice that what we do there is we go and we find the smallest element. We search through the entire list, the whole thing, and we find the smallest element. And then we move that one to the front. And you keep doing that over and over and over again. Or rather, you move your index up by 1 every time. But still, you find it, you go fetch it, and then move it to the front, fetch it, move it to the semi-front, fetch it, move it to the, keep doing that over and over and over again. But what iteration would be one move? Now, it's search and sort, on the other hand. In search and sort, through the third element on 5246, okay. See, even this stuff, I have to think about it as well, because it's been a while since I've done this. All right, so the first thing you do, right, is you would first insert 2 into the sorted left partition to get 2546, right? Because the first thing that happens there, the very first thing you do is you're assuming that everything in that left partition that you're defining is the smallest, right? So we've decided on the first pass that 5 is our smallest, right? Because we don't know the rest of the numbers. So 5 is our smallest. Then we go and we say, all right, give me the next number. The next number in this case is 2, right? So we take 2 and we shift it into place. So we say, all right, 2 is less than 5, which is in our sorted partition. So it now is 2, 5. Then that's our second. Then the third element, or the third processing piece, is we then insert 4, because 4 is the next number that's considered unsorted. And we take 4 and we say, okay, we have our sorted portion, which is 2, 5. Well, 4 is less than 5, right? So I know it's going to go behind 5. Then I'm going to say, is 4 less than the next number, which is 2? No, it is not. Now I know where to place 4. So it would be 2, 4, 5, right? So in the end, what the resulting array would look like is 2, 4, 5, 6. But it would be 2, 4, 5 that we know are sorted, and 6, which we don't know is sorted. So we still have to approach that one, and we still have to use it, right? So that's still an iteration where we say, all right, now we have to deal with 6. Well, 6 is greater than 5, so we're just going to leave it there and consider it sorted, but that still is an iteration. So hopefully that makes sense. Recursive thinking, what is the base case for merge sort? I kind of said that before, but an array length of 0 or 1, right? Because a subarray of size 0 or size 1 is just, it's just sorted. I mean, it's already sorted, right? Because it can't possibly not be sorted because you don't have anything to compare it to. So the recursion would just stop there. Why does merge sort need both divide and merge steps? Well, I mean... the reason for this really is just the divide step breaks the problem into the smaller sortable pieces, right? Because again, we're going off of this idea that if we break it down small enough, that eventually it's just automatically sorted, right? And then the merge step combines those sorted pieces into one giant sorted result. Without dividing, the problem would just simply not shrink down, right? So we're not even really leveraging recursion at that point, or the halving idea. Without merging, the sorted halves would never become one final cohesive sorted array. I mean, that also would not be helpful. Why is merge sort asymptotically faster than bubble sort on a larger n? Well, I mean, simply the reason for that is because merge sort is big O of n log n, and bubble sort is big O of n squared. That's it. And the reason for that is because n log n grows slower, like much slower than n squared as n becomes infinitely large. A good way to picture this is look up a graph that plots the asymptotics for the major big O. The major big O, like, wow, I'm blanking. The major big O asymptotics. So n squared, log n, n log n, n factorial, some constant term to the n, that stuff. And you'll see, you should be able to picture it in your head. Name one trade-off merge sort makes to achieve that speed. Well, I mean, this one is more of, I think this just is kind of implicit, but it uses extra memory during merge, right? I mean, think about how many arrays you have at that point, right? If you have an array of 10 elements, you have 10 arrays at one point in time. That's a lot. That's a lot of arrays to have all at once. So unlike simple in place quadratic sorts like bubble sort, insertion sort, and selection sort, merge sort typically needs additional space, for those temporary arrays. Java is really nice to you as well because you have the garbage collector. Other programming languages, not so much. Where if you use merge sort, it becomes even more complicated, where now you have to manage the memory. But thankfully in Java, you don't have to do that. So yeah. All right. Any further questions? Nope. Okay, cool. I'll keep moving. All right. So ADTs, linked list, I think after that, and then file IO, I think that's it. Yeah. All right. We're in the final stretch. Fantastic. Okay. So ADTs, list ADT, linked list, iterable, iterator, and bounded wildcards. This is a mouthful. So let's get into it. All right. Firstly, an ADT defines what operations are supported, not exactly how they are implemented, right? An ADT stands for abstract data type, right? It's got abstract in the name, so you can kind of infer what's going on there a bit. But it defines what operations are supported, not exactly how they're implemented. A list ADT typically supports an add, remove, get, set, size, and iteration in a defined order, right? Meaning it's just defining that you have those operations that are supported, but it's not necessarily defining how they are implemented, right? Array list and linked list can implement the same list behavior with different performance trade-offs, and they do, right? And we see that. We've actually gone over a little bit of that in this review. We talk about array list being really good at accessing stuff for the sake of like looking at it, or for the sake of grabbing the information for you to use it, right? Or even setting things. It's really fast for that. Especially importantly at like the middle of the list. But it's bad at inserting at, say, the beginning of the list. It's really bad at it. And then you also have the issue of it having to be resized when you add things to it as well at certain points. So now for linked list specifically, linked list, each node that you have stores data and a reference to the next node. This is a singly linked list. I think that's the most common one that we use in this class. It's fantastic for insertions and removals once that position is reached, right? So the main obstacle horror is for sorry about that. The main obstacle here is for is indexing, right? So getting to that position to then add something or to then remove something. That's your obstacle, not so much the actual removal or the addition of something. So yeah, I mean, it's bad for indexing, for index access, because reaching item I takes traversal, yeah. So the cost there is to the traversal to get to that item. Yeah. So, and also for the sake of like implementation and things like that, and for things that make sense, normally you just have a head pointer. Sometimes you can have a tail pointer, but the tail pointer itself is only really useful for when you're wanting to add to the back, unless you also are a doubly linked list, or a circly linked list, which I don't even know if we really talk about that. So, I guess the main ones are definitely like, if you have a tail pointer, then it's helpful to add things at the very end. If you are doubly linked list, that means that you have two references for each node, right? So you have a next node and you have a previous node, right? And you also have the data, of course. Okay, so iterable and wildcard. So iterable lets an object be used in a for each loop by providing an iterator. Iterator supplies has next and next to walk through elements safely. That's sort of like the whole reason that a for each loop even works in the first place, is because it uses an iterator. That's why it works. A for each loop is just the using the methods has next and next. That's it. A bounded wildcard, such as question mark extends shape, means some unknown subtype of shape, right? All it really does is it increases flexibility in method parameters more than anything else. You can also have a different bound. So when you have question mark extends shape, we're saying that whatever item is question mark, whatever item is going to be placed there, we are guaranteeing you that it is at some point a child of shape, right? We're saying it's a child of shape, which enables some sort of behavior and guarantees that we have certain state behavior, stuff like that. Now you can also do the opposite of that by ensuring that it is at some point, or rather it is the parent of some class, right? So if you said that it is, I don't know, question mark super dog, right? And we're assuming that dog extends from animal. What that allows for is we're saying that the wildcard itself could be dog, but it could also be animal, right? And anything above animal as well. Okay. All right, so exceptions and file input and output. So the whole point of this, or exceptions, is to handle errors very clearly and support formal logic, right? So just basically providing behavior to things that would otherwise be undefined or defined in a way that's not all that helpful, like printing out a stack trace and stuff like that. All right, so to start off with, exceptions. Exceptions represent unusual situations, such as invalid input or missing files. Right, or things just missing, or things like out of place that you don't necessarily have some sort of behavior defined for. So use try and catch to handle recoverable errors, right? So if you try some sort of block of code that you know could necessarily throw an exception, then you could catch it right then and there, right? And handle it locally. Checked exceptions must be caught or declared with throws. So a good example of checked exceptions are any of the file IO exceptions. So those exceptions there, you have to acknowledge them, right? So the way you can acknowledge them is either by trying something that could throw that checked exception and then just catching it there locally. Or you can throw at the header and have it propagate up to wherever the call site was. You can also do both at the same time, but it's a bit odd where if you do throws some IO exception, right? And then you catch it locally, you can do that, but you're still handling it locally. It's not like you're propagating it. You're still just handling it there. So it's a bit redundant. But you can do it. Throw an exception when a method cannot continue meaningfully with the current input, right? So, I mean, the good example of that is file IO, where if you get to an exception, or actually no, if you got, well, this isn't a checked exception, but still a good example is if you have an unchecked exception are things like logic errors more often than not, where if you have like a null, right? It's not very reasonable for us to expect that you're going to be able to know 100% of the time when a null is going to pop up, because it's logic. I mean, some things go awry and we're not fully privy to them until it ends up happening. So if you think there's the potential or high possibility that it will be null at some point in time once you've done an operation on it, put that in a try block. If you try it and then something happens in there where it results in null point exception, you can catch it there locally, right? And when you catch it, you can, produce some sort of message, produce some sort of message saying like, hey, no pointer exception was thrown here because of da-da-da-da-da. Like you can write that out, right? What you can also do is, and by the way, you can do a try block and not catch. That's fine. You can try something and then not catch it. That's perfectly fine. The point of that as well is that you can have a finally block, right? If you have a finally block on something, that's really helpful because you're still ensuring something happens in that finally block before we, halt everything and say, hey, we caught this exception, handle it. Like, let's deal with it. Good example of that is if we're writing to a file. If you're writing to a file and then at some point you encounter some issue, right? You definitely want to keep that inside of a try. And you can catch it there locally or propagate it, whatever you want to do. But when you try it, make sure you also have a finally block there that closes out the file writer. You want to close out the file writer because of the way that it writes the files, where it flushes periodically into the file, right? If you don't do that and you just leave it open, that file will most likely be empty and all the data inside of it will be erased. So, not good. But there's cases for utilizing the finally block. So be aware of it. All right, so file I/O. Reading and writing files usually involves checked exceptions, right? I mean, I just mentioned a few of them. Always think about opening, processing, and closing resources safely. Again, what I just mentioned about FileWriter. Oops, sorry about that. Or PrintWriter, I think, is what we actually ask you guys to use. So use PrintWriter, not FileWriter. Whatever we use in the homework, use that one. Always think about opening process. I already said that. Sorry about that. A scanner or reader can consume file data line by line or token by token. That's the you doing your scanner object dot next or your scanner object dot next line. That's all that is. Also, tokens can be defined as well. I won't go into that, but you can predetermine or predefine what a token necessarily is, or you can determine what a delimiter is as well. Normally, delimiters are white space, but the delimiter for like next line is technically the new line character. That's your delimiter there. So yeah. Yeah. I think, yeah. So a common thing that I think is not just on our exams, but period for most file input output questions on exams like this, will ask what happens if the file is missing or if something is wrong with the file, right? I think a better example of this is if something goes awry, right? What happens? What exception is caught? Does something happen guaranteed no matter what before we propagate the exception or we catch and handle it there locally? How does that all work? Yeah, I mean, I feel like those are the types of questions we'd probably ask you on the exam, more so than like, hey, this file is damaged. How can you recover? Well, I don't think we'd ask you that. So the typical pattern for the exception, sort of a blend of exceptions and file I/O, is you open the file in a try block, process its contents, and catch the file not found exception if the file is missing. You can also catch other exceptions there as well if you want, but they need to be ordered in a way where the most specific exception appears first. So that way, otherwise, if you don't do that, I think if you don't do that, you actually get a compile error. But if you don't do that, it wouldn't make sense, right? Like if you caught exception before anything else, that doesn't really, I mean, it makes sense. It is an exception, but it's always just going to catch an exception. It's never going to catch anything else that's a subclass of exception. So it's kind of not pointless, but it's not specific enough to the point where it's not that helpful. Okay. Let's check the chat really quickly. Okay. Do we need to know how to code linked list / make a linked list on the written portion? No. No. If you haven't done it in a homework, it's not fair for us to ask you to write it. For a coding question. Anything we've asked you to write, then yeah, that's definitely fair game. Like in a homework or a PE. But if we haven't done that, then no. Nope. Like, a good example is merge sort. No way we're going to ask you to do that. First of all, that would be really cruel. But secondly, you haven't written it. So it wouldn't be fair to you. Yep. Okay. So, this is ADTs, iterators, exceptions, file layout. Okay, cool. All right, so for the first one, ADTs and lists. Explain the difference between the list ADT and one specific implementation, such as array list. Okay, so the list ADT, or the list abstract data type, describes what operations a list should support, while array list or linked list or any of them that extend from the list ADT is one concrete way to implement those operations. So array list, linked list, any of those that utilize the list ADT provide the concrete implementations of it. Does not define what exactly it does. It can, like if you made your own list, whatever, like my list or something, you could define things beyond the add, set, get, all that stuff. But that's not really its point. It's more meant to provide the behavior to it. Okay. Why can two classes implement the same ADT but have different runtimes? This is because they most likely will use a different internal representation, or will use different internal representations. A good example of this actually is what we've already been talking about. An array-based structure, array list, and a linked structure, like a linked list. They can support the same operations, but with very different performance costs, right? One is definitely better at something than the other. Most obvious one there is a linked list is better at adding at the front and removing at the front than an array list by far. But an array list is much better than a linked list at getting and setting things at the middle than a linked list by far. Okay, so what methods must an iterator provide for basic traversal? That would be next and has next. Has next checks whether another element exists, and next returns the next element. Oh, and returns the next element, and it progresses the list forward by one. Why is list wildcard extends number useful as a parameter type? Well, it would allow the method to accept. It would allow the method to accept a list of number or any subclass, such as integer or double, which increases its flexibility when the method only needs to read number-like values. What is the purpose of the catch portion in a try-catch statement? It handles an exception if one is thrown in the try block, right? So this lets the program respond instead of crashing immediately, right? At least you get, a last word before it dies. It gets to say the final thing. Normally, the thing you want to say is roughly like, hey, this is where it went wrong. This is how it went wrong. That kind of thing. What exception is likely when opening a file that does not exist? Well, that would be a file not found exception. That is sort of the standard checked exception that's commonly seen in at least Java file inputs handling. Why is the file input often placed inside try with resources? Well, it automatically closes the resource when the block finishes. So this is just another way of writing it, but I don't know if we specifically say this or not, but this is an equivalent way of writing it without having the finally portion, like the finally portion to actually close the resources. So this just it prevents it does the same thing. It prevents leaks. It keeps cleanup reliable, even if an exception does occur. And that's pretty much it. Okay, so there's some practice here. For the sake of time, I won't go through it. If you all want, a little bit later today, I can maybe put something out that goes over this. But I think that most of this, you can infer this from the slides themselves, and you should be able to write like that class there and decide whether this thing should be abstract or final, stuff like that. But yeah. A few things to know concretely. Know the vocabulary for sure. So what is abstract? What does it mean for something to be abstract? What is an interface? Why do we have interfaces? What is polymorphism? Why do we use it? What is an ADT? What is an iterator? Why do we use it? Exceptions, all of that. Tie each of the structures to sort of where they are utilized. I think that's a good way of helping to remember them. If you can think of an example for something and walk yourself through it, you should be able to handle whatever question is thrown at you on the exam, because you can just configure your own example to match the test question. Definitely trace code. And trace it for if you're a compiler, and trace it if you're at runtime. That's mostly for the sake of like testing dynamic binding, testing castings and stuff like that. But regardless, trace stuff. With the time you have left, definitely go through some problems and trace. Get very solid on tracing things. For practice, explain your stuff out loud. Even if you're right, like if you are concretely right, it's already been checked, whatever, just do it, because it beats it into your head. It very much works much better than you just sitting there reading it silently. I'm telling you. I mean, there's a reason that there's an entire joke or whatever that you talk to a rubber duck in the bathroom or whatever to explain your algorithm or to explain your thinking. Do it. It works. Sort of a few next steps, or just next step for you. Work on each area. Work on your weak points, most certainly, but work on everything, because everything ties to each other, right? So if you're weak in one area, more than likely that's going to make you a little weak in another area. So just go over stuff. Make sure you do practice problems and stuff. Don't just read the textbook, or don't just read over the lecture slides. Do active examples. Yeah. And if you have time, go back over your homeworks that came out after exam 2, and maybe do them again. See if you can do them without your notes. I think that's a good indication, especially the sorting one, or the sorting and the searching one. Do that. But yeah, that's everything. So thank you all very much for showing up. I'm going to check really quickly the chat just to see if there's anything else. Yeah, if you have any other questions, go ahead and ask them, and I can answer them quickly. And then I'm going to start the AMA after. Are these slides going to be posted in the announcements? Yeah, I can post them. I can definitely post them if you want. But I'll wait for like 2 minutes for you all to ask any last minute questions. By the way, I will do one more of these for the final exam. However, I was working on something for you all to participate in that is much more active and involving with you all. That'll be more fun and more captivating than just hearing my monotone voice for like 2 hours straight. But I wasn't able to get it done in time, unfortunately. So, hopefully for the final exam, I think it will be done. So, then we can do that, and I think it'll stick in your head better as well. Okay. All right. I think I'll probably clean up these slides a little bit more. And maybe add some more active examples and active things you can work through at the very end of the slides. And then that'll be it. So, yeah, thank you all for showing up. And I'm going to start the AMA. The AMA will probably go for like an hour. And then we'll be done. Happy studying, everyone. And I'm sure you'll do great. All right. See you all.